Hey, this is Jason Molesky. In this example, we'll take a look at the binomial distribution in action. Now, Mr. Bullard's AP Statistics class did one of the examples and activities in the textbook regarding tap water versus bottled water. Now, there are 21 students in Mr. Bullard's class, and if we assume the students cannot tell tap water from bottled water, then each one is basically guessing, with a 1 out of 3 chance of being correct. Let's let X equal the number of students who correctly identify the cup containing the different type of water. First, we want to explain why X is a random variable. Then we want to find the mean and standard deviation of X and interpret those in context. And then, supposing that out of the 21 students, 13 made correct identifications, we want to know whether or not we're convinced that Mr. Bullard's class can actually tell bottled water from tap water. So first, let's take a look at why X is binomial. Well, assuming the students are just guessing, the activity consists of 21 repetitions of the chance process. So let's check the bins. Well, binary is met because on each trial, success would be a correct identification and failure would be incorrect identification. One student's result should have no effect on any other student's results, so they are independent. There are n equals 21 trials, so our number is met. And each student has a probability of 1/3 of guessing correctly, so successes are met. Since X is the number of successes in this binomial setting, it is a binomial random variable. Now to find the mean and standard deviation of X, we can actually use the formulas. The mean of X is simply n times p, so 21 times 1/3 or 7. So if the activity were repeated many times with groups of 21 students who were just guessing, we'd expect about 7 students to guess correctly in the long run. The standard deviation of X can be found by taking the square root of n times p times 1 minus p, or we get a total of 2.16. So if we repeated this activity lots and lots of times with groups of 21 students who were just guessing, the number of correct identifications would typically differ from 7 by about 2.16. Now recall, these two formulas can only be used because this is a binomial distribution. They don't apply to other random variables. Now of the 21 students in the class, 13 made correct identifications. Are we convinced that Mr. Bullard's students can tell bottled water from tap water? Well, the class's result corresponds to X equals 13, a value that's nearly 3 standard deviations above the mean. How likely is it that 13 or more of Mr. Bullard's students would guess correctly? Well, to find that probability, we can do it a number of different ways. One way to do it is to take 1 minus the probability that X is less than or equal to 12. Then we can use the binom CDF feature on our calculator to find that probability. So 1 minus 0.9932 gives us a total of 0.0068. So the students have less than a 1% chance of getting so many right if they're all just guessing. That's pretty strong evidence that some of the students in this class can tell bottled water from tap water. For some additional practice using the binomial distribution in action, try exercise 85.